So this is capsule 1 of general chemistry. It was taught at John Abbott College, and I will basically go through all the material as concise as possible. So in general chemistry, we start off with ions and atoms and isotopes, matter, compound, element, molecule, those basic components of the chemistry. There isn't anything too new. There's nothing really new other than maybe you having to know that SR stands for strontium, PD is palladium, whereas PB is lead or plomb in French, and I is iodine, Hg is mercury, Xz is xenon, Ba is barium. I hope that's how you spell barium. And Pt platinum, Ag is silver, and Cd cadmium, Au is gold. So all this is general chemistry, and this video is for unit 1 only. Other than these atoms, you also have to know cations, which are plus charged ions, and anions are the negative charged ions. So ions are charged atoms or molecules. Molecules or atoms are charged. And within the molecules, we have polyatomic ions, which consists of sulfate, sulfite, and nitrite. We also have chlorate and perchlorate. We also have CO3, so carbonate, bicarbonate, ammonium, hydronium, hydroxide, acetate, phosphate, and these are the polyatomic ions you need to know. As for periodic table atoms, so let's say this is a hydrogen, there is the Z number and the A number. The A number is the atomic mass, and the Z number is the atomic number. Atomic number represents the number of proton, always. And it could be also equal to the number of electron if neutral. The atomic mass is the mass of this atom for 1 mole. 1 mole mass of this atom. And by doing atomic mass minus the atomic number, we will get the number of neutrons. And this concept comes from the fact that each proton weighs a certain mass, and each neutron weighs a certain mass, and when we add those, it will give the atomic mass. And atomic mass just basically does not include the electron mass, because electrons are so small that its mass is negligible. I also remember the number of Avogadro. So Avogadro number 6.02 times 10 to the 23. And the periodic table, you just have to know the names, the categories. So these are alkali metals or alkali earth metals. These are transition metals, which is what we're gonna concentrate on a lot in this general chemistry course in the college level, college CGEP level general chemistry. These are covalent, or we should say non-metals here, and these are noble gases here. And we'll look at them in detail later, but there isn't too much detail we have to know about periodic table. Honestly, didn't have a categorizing questions. There's a lot about periodic table, but more of the type, or the type of elements, and grouping the elements, classifying the elements, etc. So molecules are consisted of multiple atoms, or the same atom, or multiple elements or same elements combined together. They could be different elements. They could be a bigger combination. It's just combinations of one or more atoms, one or more elements. So now we have ionic compounds, ionic, and molecular compounds. This is something we have to majorly know in general chemistry. Ionic compounds are the ions, are compounds with ionic bonds. So electron transferred to the other component, or not the component, but let's say NaCl is an ionic compound, where the Na gave its one electron to the Cl, and Na became a plus charge and the Cl became a minus charge. Whereas molecular compounds are stuff like these are molecular compounds, but it could be charged. So molecular compounds could be charged, which is something that I was confused about. But let's give another example. So CO2, for example, is a good example of molecular compound. Either way, it's all about sharing electrons. And there's going to be more about it later in the chapter. After that, we're going to learn about nomenclatures. Basically, how chemicals are named, or how chemical compositions are named. There are a few rules, starting with rule number 1. It's the binary for ionic compound with metal type 1. So the metal is a cation. It sounds complicated, but let's just jump into examples. So these are the type 1 metal. Don't need to care about what type it is. Just know that if there is a metal and a non-metal, and that these metals are not transition metals. So if you look at the periodic table, it looks like this, and as long as it is a metal that is not belonging here in this category, so I'm talking about these ones, these red ones, they follow a very simple rule of just naming it as is. So this one will be potassium chloride. This one will be sodium chloride. And that is the same for any combination of metal and non-metal, because they always follow the same oxidation state. So oxidation state means how much an atom gained or lost electrons. If it is KCl, for example, K, well, the potassium is a plus, and the chlorine is a minus, because one electron was transferred to chlorine. And that isn't always the case. I mean, the charges isn't always 1, obviously. Some could be a +2, it could be a +3, it could be a -2, it could be a -3. Usually these are what are common. But the whole point here is that no matter the charge, no matter 2, 3, minus 2, minus 3, plus 2, plus 3, if it is a non-metal and a metal. So if it is a metal and a non-metal, like this, and that the metal is alkali or alkali earth metal, and that it is not a transition metal, they always have the same oxidation state. So they always have the same charges. So regardless of the charge, you don't need to specify how many sodium or how many chloride. For example, oh, I don't have a good example, do I? Okay, so CaBr, for example. Ca is in, well, the second column, and it has a 2+ charge. So Ca usually has 2+ charge. Well, it always has 2+ charge, whereas Br is a 1- charge. That means it is going to be actually CaBr2. And to name it, well, to call it, because we're talking about nomenclature here, is going to be calcium bromide. And notice that there is nothing that we need to add to this bromide for it to have a 2 on it. And that's really because that calcium itself is alkali earth metal, and it is not a transition metal, so it only has a 2+. It only has a 2+ oxygen state. So as long as it is not a transition metal, always just name the compound with just their calcium, and then bromide, you need to just add a "ide" at the end, and no prefixes. Prefixes is what we usually use in the French nomenclature. We have like the mono, di, tri, tetra, penta, etc. These we do not need for type 1 nomenclature, so type 1 metal. And then we have, moving on, so the transition metals now. Now we're talking about all the metals and the non-metal, that the metal part is a transition metal. So transition metals have more than one, usually more than one, could have more than one oxidation state. So it means the +1 or a +2 or +3 that the atom will have as a charge after transferring it, after combining with another, let's say a non-metal atom. And that would be, for example, chromium. So chromium could be either of 2 or 3+ when it combines with another atom. So they each have their oxidation states that you have to memorize. Also for cobalt, it's also 2 and 3. For iron, it's 2 and 3. And there's manganate, 2 and 3. Copper is 1 and 2. Mercury, it's H and mercury is 1 and 2 as well. Lead is 2 and 4, and this is tin is 2 and 4 as well. So these are the main ones you have to memorize. It will depend on what your course is teaching, and there could be more or less you need to know. And when we name these, for example, a Br2, this is a chromium bromide, and we still do not say chromium D bromide because there's 2 here or anything, but we do have to say chromium. Sorry, it's a 3 here. 3 bromide. And we have to write this 3 in the Roman letter that is referring to how much the chromium, how much ions the chromium will have after it's combined with bromide. So the 3 is talking about the 3 plus that the chromium will have. And since bromide is a -1, it will have a 3 here. It does not mean that this 3 is automatically talking about the bromide. It doesn't. It just did because it's a -1 for bromide here, but it could be another compound that has other charges than -1 for the anion, and in that case you won't necessarily see the Roman number matching what the covalent or what the non-metal is having as oxygen charge. And these will also work for polyatomics. So let's say this one, HgNO3 2. So mercury, in this case, will be a mercury 2. Nitrate, because nitrate is once again a -1, and since there are 2 plus on the mercury, well, there has to be 2 and nitrate for the balancing to work and to cancel each other out. And then now we have the ionic compounds. We're still talking about nomenclature, ionic compounds with polyatomics now, so I sort of talked about it here, but polyatomics just comes in with themselves, like their names themselves being added to it instead of the atom name and the "ide" afterwards. For example, NaNO2, well, we know that NO2 is nitrite, so sodium will be a +1 and nitrite will be a -1, so this is just sodium nitrite. Another one, FeSO4. So SO4 is sulfate, and sulfate is SO4 2-, whereas the iron has either 2 or 3 charge. But looking at this, we know that it's a 2 charge instead of 3 because we have a 2- at the sulfate, and there is only 1 iron and 1 sulfate. So in this case, the name will just be iron 2, identifying the 2, sulfate. As for oxyanions and the oxyanions are the anions that have oxygens. There is a very simple rule of 8 and 8. So let's say nitrite and nitrate. This one always has less electrons, and this one has has less oxygen, and this one has more oxygen. So nitrite, nitrate, and sulfite, sorry. Now talking about hydrated ionic compounds, or people call it hydrates. It is a very simple rule of just adding a dot and the prefix and then write hydrate. This is something like BaCl2 dot 6H2O. It could be a chemical that has H2O after their name with a dot in the middle, and the 6 is the prefix that we're going to use for, so here it's going to be a hexahydrate. And in the front we have a normal, well, not a transition metal, so this is going to be barium chloride. Nothing needed for the 2 because barium is always a 2+, and it doesn't mean that, no, there's no Roman number here. So then we need to add a dot. Well, dot is actually only for the formula, so you don't need to write the dot in the name itself, but in the formula you do write the dot. This is barium chloride hexahydrate. So if you see the name instead, and if you see the name but you don't see the formula instead, you just have to memorize or remember that you have to add the dot in the middle when you see the hydrate. So there is a little bit of a tricky part when it comes to molecular compound naming for nonmetals. We use prefixes, and that is it. So this is like the French version of the nomenclature. It's very easy, honestly, for me. But let's say a NO2 or a N2O. We're giving specific these 2 examples because NO2 tend to look like nitrite, and that isn't the case because there is no charge. If there's no charge, it isn't a polyatomic ion. It will just be nitrogen dioxide. Notice that both are non-metals, and if it is a non-metal and there is a prefix or there's a number that's identifying how many of the atom there is, you have to specify what they are, but you usually do not need the mono. So the mono, in rare cases, well, I have never seen a mono in the front, like the first compound, the first atom, but usually in the second atom there is, if it is a single one. So for example, this one, it's gonna be D-nitrogen, since nitrogen does have a 2 right there, and monoxide. Really simple, just using the prefixes. So there's the hemi, which means half, but you don't really use it. Mono, di, tri, tetra, penta, hexa, hepta, octa, and nona, deca, and that's pretty much it. Now you need to know some acids. Acids are basically hydro something, whereas the hydro either ic, usually ic, you have to add the ic at the end, and you say acid. So for example, HF, AQ, there will always be an AQ when it comes to acids, because it just will. And this one will be hydrofluoric acid. So you need to add your hydro, and then you add the ic, and then you add acid. HB, AQ, very similar, hydrobromic acid. And the ic terminaison here isn't always ic. It depends on what you're naming, but usually it will be ic. When would it not be ic? It will be not ic for oxyanions, oxy acids, I should say. So oxyacids, for anything that ends with 8, you still use ic acid. And for ite, you use os acid. Sounds goofy. Os acid. And these are non-metal and the oxygen. So let's say HNO3AQ. This is going to be a nitric acid. So realize that there is no hydro here. There's no hydro because these are polyatomics. If you see a polyatomic with a hydrogen in front and it is acid because it's aqueous, do not add a hydro. I do not know why. Now we have, let's say, HNO2AQ, for example. And this one will have a 2 right here. No, sorry, no, it does not. It's a STU -1 and a +1, in this case, -1 and +1. This is going to be nitrous acid. I was talking about a sulfate instead. So let's say a sulfite, actually. Let's use a sulfite. So here we'll now have a 2 because sulfite has a 2-. So hydrogen is a plus and it needs 2 of that to equalize. This one will be sulfurous. Sulfurous acid is coming from the sulfite. Why is it a pH? I think it's a F. I'm not sure, maybe it is a pH. Either way, this is sulfite. And if it was a sulfate, you use ic instead. So the aqueous sign indicates that it is an acid. In the nomenclature section, I don't think it's all of them. Now we're going to learn about the next section of Unit 1, which is formula. Masses, moles, ppm, ppb, molarity, dilution, and just lots of more stuff. So just remember that moles are 6.02 or 6.023 times 10 to the 23 units. ppm and ppb is particles per million and particles per billion, and these are units of units, but when we use them, we'll usually use grams. So it will be a gram over gram of some sort of substance over another substance that we're comparing it to. So just remember these two are of grams over grams. Molarity is, oh, that's really badly written. Molarity is the concentration of mole per liter, always. Dilution is just the concept of adding solvent. Adding solvents, so it will become more diluted. More diluted means the concentration is lower. So then the dilution part, there is a handy equation of M1V1 equals to M2V2. So the molarity of the first solution times the volume of the first solution is equal to the molarity of the second and the volume of the second, and that is just the formula that always works for, let's say, a certain substance that is transformed into another substance, and we're given 3 of these and you're looking for 1 of them, then you can just use this formula to find it out. And the whole point of learning these is they're going to give you either one of these guys. So it could be a concentration ppm or ppb, moles, mass, and dilution. Oh, I just forgot to say that ppm is for millions, so 10 to the 6, and ppb is of 10 to the 9. And that could be given as moles, and you just need to convert the moles into a gram over the gram of the solution. not the solvent, solution, so the solute plus the solvent, and that times 10 to the 6 if it's a ppm, 10 to the 9 if it's a ppb, and you will get your ppm or ppb concentration. You have to make sure that there is no units after the ppm or ppb, because ppm and ppb are the units. They are the units. And the question that you're going to get a lot on the final and prior tests is to basically juggle and convert between all these. So these guys all need to be converted amongst each other. They could give you one of them, and maybe even just give you one quantity, and you have to turn it into molarity, turn it into the moles, and ask you to do dilutions. Now we can do reaction stoichiometry. This is all about the formulas, the chemical formulas. Let's say there is a 2CH18 plus 25O2, 16CO2 plus, it's a hydrate over here, 18H2O. Everything here, each components, are proportional to each other with their coefficients. So let's say if you have 3 of the CH18, how many CO2 will you have? You can find that out by doing 2 over 3 equals to 16 over what? Or more precisely, you should write it as 3 moles of CH18 equals to 16 CO2 divided by 2 CH, not equals to, times H18, and you realize that these cancel out, so then you just do the multiplication and then divide it by 2. Will give the number of CO2 in moles, and this works just as a cross product, and I'd say this is a very, very easy concept. After this, you can start learning about reaction yields. So reaction yields, the word yield will be brought up a lot, but you have to know something called the limiting reagent. Limiting reagent, the word reagent means reactive in French, but reagent is the reactants. So let's say in here the reactants are O2 and C8H18. I do not know the name specifically for that, but limiting reagent means whichever one that is going to be left over. Just know it, remember it as leftovers. Reactant. And we can find this out by searching for the number of moles of one of the products. So you can go like, if there's 2 C8H18 and everything is used, how much product would that give? And you can use either CO2 or H2O. If you use 28 moles of O2, how much CO2 or H2O can we have? And one of them will be higher than the other, and you always have to find the lowest one, and the lowest one will be completely absorbed, so it is the limiting reagent. I'm totally confusing everything. Limiting reagent is the one that limits the reaction, so it's the opposite. It's not the leftover, it's the one that is completely consumed. Complete. And if it is completely consumed, it is limiting because the other reactant will not be able to will use it itself completely into the reaction, so it will be just floating in the solution. For example, let's say there's a reaction, this is a solid, and there is some stuff that's floating in here, and those are the leftovers. And the limiting reagents are all reacted, are fully reacted. So to find this out is just what we did previously, cross products and looking for the number of moles of products each reactant can make. And to do that, we're going to use a table that just does the mass of initial, reaction, and final. And there is usually the reactant 1, the reactant 2, and one of the products that they're going to usually tell you, and it's going to be usually a precipitate. So the precipitate product, meaning the product that becomes a solid. And that's what we usually look at because it is more easier to identify and usually more obvious in terms of the mass. So one of them will be bigger and one of them will be smaller in terms of how much products each given number of mole of reactants can give. And the one that is smaller, so the smaller product made after doing your cross product, is the limiting composition, limiting reagent. And the one that gives a bigger number of product, well, then that guy is going to be an excess reagent, meaning it's going to be a leftover product. It's all about which of the reactants is going to be fully used and which one not. So now we could talk about the theoretical yield. The theoretical yield is the amount that can be made from a certain reaction. So it's exactly what we just talked about here. The smaller number of mole of products, so made by the limiting reactant, the LR, the limiting reactant, the smallest reactant that's going to be fully consumed. After it is fully consumed, how much product does it make? That amount of product is the yield. The word yield means how much product was made from the reaction. And there's something called we should actually finish talking about the theoretical yield. So theoretical yield, there are ways to express it in moles or mass. It is fairly simple. If it was in moles, you just need to give the number of moles you had here and answer that you had a certain mole of CO2, for example. If it's a mass, you just need to convert it into mass from the periodic table by looking at the molar mass for 1 mole is how much, and you just convert that into the number of moles you had into a mass. Now that we know what theoretical yield, well, theoretical just means calculated yield. So if all of the reactants are used in the LR, the limiting reagent, and just the reaction is perfectly performed, I don't know how to say that. If the reaction was perfect and there's nothing lost, nothing evaporated, nothing was gone missing, nothing was spilled out in the reaction, which is not possible in real life, then the amount of mass will be this, and that's the theoretical yield. In theory, the yield, the product should be this amount. And of course that's not true, so we have to learn something even more complicated, well, not that complicated, called percent yield. Percent yield is, maybe you already can figure it out, the actual yield, so the real life product amount divided by the theoretical yield that we just found. So in theory, if nothing was lost, that's how much it should be, times 100% to find the percentage of products that were made products. So if the percentage is higher, we lost less, so we gained more. So the reaction didn't lose too much, lost less reactants, or the product was more the reaction was a little more fully done. And if it was a lower percent, that means we lost a lot of components, a lot of reactants. So the questions will be in the style of giving you a formula. So let's say TiS plus 2Cl2 gas, that gives a TiCl4 solid. They go like, which component was limiting? So which reactant was fully reacted? They will give you that we had 4 moles of Ti, let's say 10 moles of Cl2, and we want to know how much product it will make. And by using stoicheo, so 4 Ti will give, 1 Ti will give 1 TiCl4. That means, 4 moles will give 4 TiCl4. So clearly here, if Ti was fully consumed, it will give 4 moles of the product. If the Cl2 was fully consumed, 10 moles of Cl2, how much would that give as product if 2 Cl2 will give 1 TiCl4? So you can see that that just becomes the half of it. So if it was Cl2 that was fully reacted, we will have 5 moles of the product. We can see that Ti is much smaller, 1 mole smaller, so this is a smaller one, and that is the limiting reagent. That means it will be fully used up for the reaction. So this one, Cl2, will be in excess. That's what we're trying to calculate. And now that we know that 4 moles will indeed be the theoretical yield, of this reaction, meaning we'll have 4 moles of TiCl4 if the reaction was perfectly successful, and they could give you the mass of the real yield, actual yield is, let's say they said a certain gram, and you need to look for, the question's asking you the percent yield. So what is the percentage of the gram of how much product you actually got divided by the grams of product that you calculated from the theoretical yield times 100%, and that's the percentage you're going to get, and that's your final answer. This is a very simple context in general chemistry. Other than that, you definitely need to know to write your equation. So balancing equations. This is purely from practice and maybe logic and maybe some talent if you have, but they will be a little more complicated in high school stuff. And an example could be, well, I don't have an example. Just try to balance stuff. We're not going to spend too much time on it. It's not too hard. Now we're going to talk about percent atom economy. So percent atom economy is only touching the formula. So let's say we have this formula here, and we are asked to find the percent economy of creating CO, let's say. So the percent economy is a way to calculate how efficient we are, or how ecological we are, how environmental friendly a reaction is, meaning how less of waste are we making. And we can see that by looking at how much reactant, or how much product was made from how much reactants that reacted. So how much reactant we use. And we're going to use mass unit of reactants. and the mass unit of the desired product, because not all products in the lab are the desired ones. Usually only one of the products are desired to be used for maybe that's the final product. Maybe we need another step and we're going to use that product for another reaction. The whole point is to add up the molar mass of each component in the reactants and add up the molar mass of we said that we want to make CO, right? Okay, so this is the desired product. So add up your, let's say here it will be 16.04 gram and H2O will be a 18.032 gram, and add it up they will give a 34.06 gram of reactants that were used, whereas the product was, that's a 12.01 plus in this case would be 2.16, so that gives 28.01 grams. And sorry, I totally messed up. It will not be CO. We used H2 instead. So the H2, yeah. H2 is a 6.05 here. And this is the grams of product made from this amount of reactants. And all we have to do is divide that. And then we have times 100 to find the percentage. And that percentage is 17.2%. And that means the product was only 17.2% of the reactants that we used, meaning whatever other percentage of the reactant was gone to waste, to carbon, the CO. And this is very uneconomical, so this reaction was not economy friendly reaction. The higher the economy percentage, the more economical, or I should say eco-friendly the reaction is. So let's say if it was a 98%, this means that 98% of the reactants turned into products. That's all that means. And you don't need any number of moles or the number of mass in grams given. It's just the formulas. So if you only see the formulas, that there's nothing wrong with it. You just need to know that you add up the total molecular mass, molecular weight of each reactant, and then the desired one in grams, divide it, and it's times 100 to find a percentage. And that's it for the first unit.